Welcome to this meeting is being recorded. And of course, just the usual housekeeping announcements of please mute if you're not actively speaking. That said, we do encourage people to be participatory in this. We've got 75 minutes or so, and I'm going to take up the first chunk of time or so to kind of give an overview of a couple of things, the benefit of doing in situ reconnaissance of planetary bodies, and then talking about a compromise payload between what we've been hearing about, the whole heliophysics, the heliophysics baseline payload and the full planetary augmentation. And after that, we're going to open up a Google Doc for concurrent joint editing and brainstorming. And it'll really be kind of in that time that I hope we can have a lot of conversation and discussion. That being said, during my main presentation, feel free to speak up. There's always the chat to put things in as well. My thanks to James Mastandria, who is helping to host this and kind of do some of the shepherding. And also a tip of the hat to Charlie Dedelich. She and I have been collaborating for a couple of years, and she's going to be our note taker, and she's finishing up her master's degree at University of Alaska Anchorage, North Carolina campus, and is looking for PhD programs. She's our note taker, and so I'm going to go ahead and try to screen share. Zoom seems to curse me in that my sharing of screen commonly freezes. And so I'm going to be frequently calling out the slide number, and Charlie will rescue me if it really freezes with that. So go ahead, and we're starting on slide 1 here. Can you all see my screen?
Yes.
Okay, great. Okay. So first I want to make the case that single planetary flybys are revolutionary. And with moderate augmentation, we can really get the goods as we fly by one of these planets. So distant astronomical observations are excellent for a few things. That would be, and I'm talking about here of like trans-Neptunian objects, specifically dwarf planets. And for sake of convenience, I'm defining a dwarf planet as any solid body greater than 400 kilometers in diameter. That's generally the diameter at which icy worlds become round. And distant astronomical observations from Earth are really great at global composition, spectroscopy, getting the size and shape from stellar occultations, and also from high phase angle imaging, like what New Horizons has gotten for us in the middle of the Kuiper Belt, and also getting the spin and albedo. But that's about where their practicality levels off. And you really do need single flybys to understand a planet or other world, because they really change our view literally overnight. I'm on slide 3 now. On the left-hand side, we have one of our best images of Pluto from the Hubble Space Telescope. And then almost literally overnight, the image on the right shows what our view of planet Pluto was transformed to by having a spacecraft fly by. And the length of that encounter, where we were able to get geophysically meaningful data, being able to resolve things like a nitrogen ice glacier, cryovolcanic constructs, 10,000-foot tall water ice mountains, the stably stratified visible atmosphere. This required a spacecraft to spend just a few hours in the vicinity of the planet.
Kirby, do you want questions as you go, or comments, or do you want to still hold?
If there's something that you really want to dive in and say midstream, that's fine. But yeah, I mean,
and we made this case many times when we were working to get a mission to Pluto, but this has been the case for every first planetary flyby from the early 60s with Mars and Venus to the first flybys of the giant planets. Everywhere across the solar system, first flybys have been transformative, and they've usually shown that what we thought we knew from Earth was very naive and usually wrong, in fact. So this is just another example of it. You're making a case that's very easy to make.
Yeah,
a lot stronger than just with Pluto.
Yeah, well, thanks. Pluto has a warm spot in my heart, as you know. So I should get back up and give some of the rationale for making this case. This is a very broad group on the Interstellar Probe team. There's a lot of people with mostly backgrounds in space physics and heliophysics, and sometimes it's not always obvious to all of our colleagues the value of people who don't necessarily work in planetary science. It's not always obvious that the value of planetary flybys is high as it is. And we've had some experience presenting to some space physics colleagues where we needed to make that case. So,
and I'm just saying you can make it a lot stronger than a one-off on Pluto, because it's been the case everywhere across the solar system without exception. You can even do it with small body first missions like Galileo and Gasper that discovered the first satellite of an asteroid, and they turned out to be ubiquitous.
Yeah, absolutely. Yep, thanks. So just wanted to make that point that for an unexplored target, the science value is relatively decoupled from the time spent collecting the data. Now, in terms of Interstellar Probe, what it can do, we're on slide 4 now. You know, our solar system is incredibly diverse. Whatever you learned about the 8 or 9 planets, get that out of your head. Dwarf planets are the most common type of planet in the entire solar system. And we've really only flown by, in the trans-Neptunian region, 3 of these planets, Pluto, Charon, and Triton. And so there's a lot of potential here for transforming the field of comparative planetology in this 3rd zone of the solar system beyond Neptune. And also flying by a small planet is really a boon to planetary science in general. Carly Howitt and others did a really great job over the summer showing how resource and time intensive it would be to send an orbiter to one of these planets. The amount of resources and the time it takes is maybe is pretty constrained in the present time. And so flybys for at least the foreseeable future are really the way to go to really explore this vast reservoir of planets. But missions to the trans-Neptunian region are of course rare and expensive. And it'd be a loss to planetary science for some kind of planetary imager to not hitch a ride on Interstellar Probe on its way out of the solar system. And I also want to make the case that there's huge public interest for planets and for images of these far-off worlds. The public loves planets, you know, from huggable Plutos to being above the fold on the New York Times when New Horizons flew by Pluto and gave us our first up-close images there. This really captures the public's imagination. And even for a spacecraft that has heliophysics as its primary mission objective, the planetary science will create what educators call a mental schema, kind of this context for understanding perhaps the more esoteric area of space physics. So with kind of that as a prelude, now on slide 6, I want to talk about what I've been calling the Helio Plus planetary augmentation compromise. And the overarching trade consideration here is that most of something is better than all of nothing. If we can't have the full planetary science augmentation that Jim Kinnison and others have been mentioning on this, then we'd at least love to get a majority of what you could do with a planetary augmentation. Now, the baseline heliophysics augmentation or the baseline heliophysics mission, as you'll recall, is a sun-pointed spinner, where the high-gain antenna stays fixed, rotating, pointed at the sun, and it's an in situ particles and fields mission. Putting cameras on spinning spacecraft is hard. It's not impossible, but it's hard. Generally, the concept of operation for this sort of thing is a push broom camera, basically a line or a short line of pixels that looks perpendicular to the spin of the spacecraft that builds up an image as the spacecraft rotates. And they generally look about 90 degrees to the spin axis. The Pioneer 10 and 11 spacecraft with their photopolarimeter imaging experiment were examples of this. And of course, Juno is the most famous current example of this, where Juno Cam takes these beautiful images of the cloud tops of Jupiter. And Juno Cam on Juno is often used as a potential analog to what Interstellar Probe could do if Interstellar Probe were a spinning sun-pointed spinner. But it's not exactly analogous. In the case of Juno, the camera has a 58-degree field of view. This is about half your human field of view. The spacecraft also gets within just a couple thousand kilometers of the cloud tops for a planet that's 140,000 kilometers wide. From this distance, Jupiter fills the field of view, taking up over 170 degrees of the sky. In other words, you can't miss your target. Just point your camera over there somewhere and you'll take a picture of the target. Now, for an interstellar probe flying by a roughly 1,000-kilometer diameter dwarf planet at 36 kilometers per second, in order to image the surface at a reasonable pixel scale of kilometers per pixel or better, it's going to have a much narrower field of view of just a few degrees or less. We're going to be flying by within a few thousands to tens of thousands of kilometers. And of course, the target's pretty small. Furthermore, if it's a sun-pointed spinner spacecraft, it's going to be rotating. I got ahead of myself there. I'm on slide 8 now, if this is still updating. We're going to be rotating between about 1 to 5 RPM. And in one revolution, if we're traveling at 36 kilometers per second, we're going to travel almost 2,200 kilometers in those 60 seconds. And of course, we're looking at Charon-sized planets, about 1,000 kilometers. And the phasing, that is getting the spin of the spacecraft to line up with where the spacecraft is in the field of view, is really hard. It's relatively invariant, but depending on the field of view, the angular resolution of a single pixel, what we call the instantaneous field of view, and where the spacecraft is in its passage by a planet, there's about 15 seconds in the 50-year-long mission where the planet would be where you'd want it to be to take a picture. And you better hope that the spacecraft is rotated properly to be able to image it in that 15-second window. What I'm trying to say is the chances of missing your target are unacceptably high in this concept of operation where you only image at closest approach. I've tried to schematicize a little bit of that here. I'm using Quaoar as a stand-in here. It's a little over 1,100 kilometers in diameter. And I have shown the size of the planet as to scale with this distance of a 10,000 kilometer notional flyby distance. That's on the order of New Horizons flyby of Pluto. The yellow lines are how far the spacecraft travels in different periods of time based on different rotation speeds. If we're at 1 RPM, the spacecraft traverses way more than 1 planet diameter. If we're at 4 RPM, we traverse about 1 planetary radius in that.
Kirby, sorry, this is James here. Am I the only one saying I think your screen froze during the animation?
Very likely.
Yes.
Can somebody else confirm?
You want to take over right quick?
Sure.
Charlie should have slide 8 up with the animation already played.
Yep, I'm working on that.
Yeah.
Yeah, we don't see anything in the bottom right of the screen.
So I stopped sharing. Go ahead. Yep, there we go. Thanks, Charlie.
Yep, no problem.
Okay, so the yellow lines are how far the spacecraft travels in different periods of time, depending on how fast it's spinning, 1 RPM or 4 RPM. We're talking about a significant fraction or multiple even of a planetary diameter. The white lines on the left are the fields of view from different cameras, baseline for this situation. If you use a camera that has similar optics to New Horizons LORRI camera, you'd get great resolution at 50 meters per pixel if you can hit the planet. If you had the Ralph Envik camera, you could probably image the entire planet. Although if you look at the geometry here, the closest approach happens over the planet's terminator, the line between night and dark. And so half the planet would be in nighttime darkness, and you would have missed half of the sunlit hemisphere. So this just hopefully goes to show that taking images on a spinning spacecraft can be hard. If you go to the next slide, please, Charlie. So a few issues that to mitigate this related to a spinning spacecraft is you could have, yes.
Can I ask a question? So I might get lost as you carry on, if not. Are you basing that on the idea, on the previous slide, on the idea that the spacecraft is spinning at a certain amount so that it's going out of our field of view? Or is it simply the speed as the spacecraft goes past the object? And you're assuming the camera's pointing at it the whole time?
Yes, I'm assuming, so I happen to have a model of New Horizons here as a stand-in. If there's a camera pointing out, looking 90 degrees, and this will get to Casey's question in the chat as well. If you're looking out 90 degrees from the RAM direction, you're only imaging at closest approach.
Right, so you're not, so it's the spin axis is perpendicular to the look axis of the camera.
Yeah, that's what I've tried to show, just like on Juno. Yep. And that assumes a somewhere between 1 to 4 RPM, which is kind of the spin rate the engineers have baselined. So Casey, hopefully that addresses your question as well. And yeah, Casey, I'm going to get to what you're talking about. So one ways of mitigating the problems of a spinning spacecraft is to perhaps have a despun camera or a despun platform that rotates opposite the direction of the spacecraft. You could consider a daughter spacecraft, like a large, like a multi-unit CubeSat or something. That could be jettisoned. You could have multiple redundant cameras so that you guarantee to have correct phasing between the spacecraft spin and the closest approach. Charlie, if you'll hit return one more time. All of these issues, these are possible solutions. There is a certain amount of complexity associated with these, things that can break on a long mission, things that may have to be qualified for cold temperatures, and a lot of mass. For instance, having redundant cameras, for hoping that one of them gets a picture, that's a lot of thrown away mass on a spacecraft whose primary mission is heliophysics. hit enter one more time, Charlie. But I want to consider a camera that stares straight ahead on a spinning spacecraft. That's something that hasn't gotten a whole lot of attention, but it's a simple, elegant solution that doesn't have any moving parts and that doesn't have the complexity in mass, comms, power, propulsion of daughter spacecraft or despun platforms. So next slide, please. If you consider a nose camera on a sun-pointed spinner that just stares straight ahead, and we use a camera inspired by the New Horizons Ralph MVIC camera with a field of view of 5.7 degrees, and that just looks straight ahead parallel to the spacecraft spin axis. At about 45,000 kilometers away, the entire sunlit hemisphere of the target planet, in this case Quaoar, will fill a quarter of the field of view at a pixel scale of better than a kilometer per pixel, about 800, almost 900 meters per pixel. As the spacecraft closes on its range to the target, hit enter one more time, Charlie. One more time. About 7.7 minutes later, assuming 36 kilometers per second, at a distance of 28,000 kilometers away, a quarter of the planet will be imaged at about half a kilometer per pixel. Mm-hmm. Now, some of the advantages here is that the planet is always in the field of view of the camera post Jupiter gravity assist, because after Jupiter gravity assist, we're headed almost in a straight line towards the planet. This would also assume a very close flyby of about 1 planet diameter from the surface of the planet. And another advantage is that you could image the entire planet at varying resolutions, but depending on the planet's rotation speed and axial tilt. So just like we did on New Horizons on approach to Pluto, we imaged what we call the far side of Pluto. It was at much lower resolution than the encounter hemisphere, but it was better than anything else we had. And Quaoar and another potential planet, Gong Gong, rotate significantly faster than Pluto, which has a 6+ day rotation period. And so there's a chance we could image a fair swath of the planet just on approach with a nose camera. This image on the lower left is a comparable view from New Horizons from 35,000 kilometers away on approach. If you go to the next slide, Charlie, on slide 11. Here's that image again. This is from 35 kilometers. This is from 3 times the closest approach distance. It's better than a kilometer per pixel resolution. This was taken about 27 minutes before closest approach. And if this image, along with all the spectral channels in a spectral image cube, if this were all that was taken from New Horizons, if we didn't get any other pictures closer to Pluto than this still would have been enough to revolutionize our view of Pluto and dwarf planets in general. This resolution, this pixel scale, is good enough to to construct a global geologic map, begin to understand the stratigraphy of the planet, understand the distribution of different compositions. Now, of course, in the case of New Horizons, the LISA component of the Ralph camera, the infrared imaging spectrometer, had coarser resolution than this, but this is still good enough to get global distributions of different compositions. I've blown up on the right here. This is enough to discover things like cryovolcanic edifices, the Sputnik Planitia nitrogen ice glacial carved valleys in the highlands, the tholin-rich equatorial region of Cthulhu, canyon-like grobens. If this image, if we didn't get any images closer to Pluto than this would have been enough to justify the mission from a geophysical perspective, at least in my opinion. Next slide, please. And Alan, correct me if I'm wrong, but roughly beyond that dotted line there, it would not be seen at closest approach because the spacecraft would be flying over the terminator. And so the advantage of imaging the planet on approach is that you see the entire sunlit hemisphere as presented to the spacecraft.
Kirby, one thing that we didn't include on New Horizons, but we could include on any future Kuiper Belt mission, is a low light level camera,
okay,
which is capable of seeing in the dark, just the way that, for example, military forces wear low light level goggles to see only by starlight.
Wow.
So you actually want a light amplifying camera, or maybe some sort of.
If you do it with an image intensified camera, exactly.
Yeah.
Okay, that's good to know. That's a sort of great.
I'm flying one on Virgin Galactic for
Are you
another
really?
reason. Yeah.
Well, I'll be interested in the results. I assume there's a resolution loss.
It depends on how you design it.
Okay.
You can achieve these resolutions.
Okay. Well, I'm glad to know about that, Alan. Thank you.
Kirby, I want to make one other comment. Since you and I were just talking about this, you don't have issues with smear, or smear is rather mitigated or small when you're this far out and still heading straight towards the object.
But
That's
you
another
will
thing
have you will have smear issues. Your resolution, I don't believe, took into account the fact that the camera is going to be spinning about its central axis.
That's a
anticipated my
different
next
sort of
set
smear,
slides.
rather than the velocity relative to the object. And the smear you would get when you're closest approach, trying to look 90 degrees. That's going to be huge.
Right. Well, if we're looking, yes,
Now,
you've
right.
the
There's
next set
another
of
smear.
slides, actually. Yes, the zoom smear is going to be pretty small. The biggest source of smear is going to be from the rotating spacecraft. Absolutely. Next slide, please.
And if Juno solved that problem, hopefully.
Yeah. So I just want to point out that these global views of Pluto and other satellite planets is similar to what Voyager got at Miranda from similar distances between 30 to 40,000 kilometers away at basically half-kilometer pixel scales. It's good enough to see these canyon-like grobens. It's enough to see the coronae, these rectangular features that implicate perhaps mantle convection in very small icy planets. Next slide. And it's also very similar to what Voyager 2 saw 3 years later at Triton at 600 meters per pixel from 40,000 kilometers away of the sunlit hemisphere. And this was good enough to discover these plumes, spreading centers, the cantaloupe terrain, which is also probably near surface convection within the crust of different densities of ices, enough to see sublimation cliffs, craters, cryovolcanic plains, and collapse pits. Although, of course, with Voyager, there were poor compositional constraints since it lacked an infrared spectrometer. And Interstellar Probe could improve on this on its flyby target.
And Kirby, let me point out that crucial to any of these types of flybys is getting stereo so that you can determine what's up and what's down and by how much. Those geysers, for example, on Triton would never have been known if it wasn't for the fact that we could do parallax and determine that they were really suspended above the surface.
Good point. Thank you. Yeah, and as the spacecraft closes on approach, you know, a series of images would allow for improving stereo baseline, even I think on a nose spinner.
Just bake it into the cake when you're making the presentations to others.
Yep, thank you. Great. Next slide. Now here's what a nose camera would miss. This is, the nose camera, of course, is not pointed 90 degrees, and this is what we would miss. For example, using Pluto again. We would miss better than 100 meter per pixel spatial resolution. We would miss low sun angle images that can show a lot of relief. We would miss look back images of any atmosphere or plumes. And we would miss thermal infrared temperature maps using the high gain antenna.
You would miss the composition.
I mean, we would have some composition, right?
Maybe. I mean, you could have a methane filter or something simple, but you know, the really big advance of New Horizons over Voyager, or you could do a Gedanken experiment. What if you took Voyager to Pluto? What you'd be missing is the LISA infrared mapping.
I'm assuming a LISA-like capability on approach in the nose cam.
Oh, I didn't get that out of what you said. That's
No.
great. I'm glad to hear that.
I thought you had
It's in my next
photometric.
slide. It's in my next slide. But just to finish up on the previous slide, Charlie, yeah, that strip down kind of diagonal across Pluto is what the Lori camera, again, a panchromatic, it doesn't give compositional information, is the sort of thing we would miss with a nose camera because we would not be imaging at closest approach. Next slide, yeah. What about smear? We're traveling 36 kilometers per second. Most exposures are on the order of 100 milliseconds, 1/10 of a second. But the zoom in during a 1/10 of a second is that you travel 3.6 kilometers, which is a very, very small percentage of the total distance. And so the zoom smear is probably less than a pixel. By far, the biggest source of smear would be tens of pixels from the rotation of the spacecraft. And so there are some ways around this. Now, this folds in, and Alan, probably earlier, I should have, maybe it would have been better to put this earlier, but if your camera is rotating, there may be a way to do curvilinear time delay integration, where instead of just co-adding along a line of pixels, you're doing it around a circumference on the detector, on which you could also place different filters. This is a novel way of doing things.
Sure.
I don't think this has ever been done before. This would be a unique use case, and this is the largest risk. And this would be a significant software engineering challenge. You would have variable pixel co-adding as you move further out along the radius of the imager, which I've just shown a cartoon of on the right. You'd have variable exposures. How short could we get the exposure time to keep the signal to noise ratio greater than 100? Of course, you could have arbitrarily, depending on the pixel sensitivity, you could have arbitrarily number of visible and near infrared filters on there to still get compositional information. Some other issues, could we just mechanically despin the focal plane CCD or CMOS detector and only do that when we're taking images? That would eliminate this problem, and we could go with a camera maybe closer to the ICE camera, or there would be other schemes for getting multispectral data.
What does Juno do?
Juno's a line scanner, and so it's conceptually the same as Ralph Emvik or Lisa in that regard, in that it's a line of pixels that have different filters on top of them.
Is it a rotating spacecraft or is it not?
It's a rotating spacecraft, but it's looking 90 degrees as opposed to looking parallel to the bore site. Looking parallel to the bore site and having this kind of radial or curvilinear time delay integration is novel, and I don't know how realistic it is or not, but I'm throwing it out there as an idea. So next slide. So I think this is my last slide. The further considerations and take-home lessons is that with a nose camera, because the planet is only imaged on approach, uncertainty in the planet's radiosolar distance is not as important as it would be for imaging at closest approach. From a solar illumination perspective, if Quaoar is our baseline planet, that's at about 45 AU from the sun. That's the same distance as Arakoth was for New Horizons. We've done this sort of imaging in these lighting conditions before. One could also consider a trade space in which the camera is somewhere between 90 degrees and parallel to the rotation axis, where you're sweeping out cones. That has some different trade-offs. The geophysical and compositional results would be comparable to New Horizons on approach to Pluto and Voyager 2 at Miranda and Triton. And there would be certain sacrifices for higher spatial resolution, atmospheric searches, and low sun images. Now for most of the rest of our time together, I want to transition to our Google Doc, which I'm going to put a link for right now in the chat. And what I really hope happens is that all of your wonderful people's expertise will really come to bear in this Google Doc that we can edit concurrently in real time, and that this will spur a lot of fruitful discussion. There are, based on what we've said here, my intention for the rest of this, of the rest of our time together, is that we have verbal discussions on here, but feel free to just kind of move on to just reading through this document, adding your own thoughts. My only request is that you not delete anything that's there. Don't delete anything we have or that someone else writes. By all means, disagree with someone, but please don't delete anything. We're going to leave the spreadsheet up until December 1st, so that if something strikes you in the middle of the night on Sunday morning, you can go ahead and add it. I'm going to go ahead and try to share my screen again, showing this, but by all means, feel free to click on the link. You do not need a Google account to access it. Hopefully you can see my screen now. And I'm just going to go through a top level, just kind of discussing some of the top level points I hope we can discuss, and that people can start writing toward on the document. Also, if you don't want to add something directly on here, go ahead and highlight some text and go to insert comment. That's also a very useful way of capturing ideas. But the first part, there's hopefully you can keep in your head. I want to think about both. This is more focused on the science. So whether we're doing a Helio Plus with the nose camera or a full 3-axis stabilized planetary augmentation version of the spacecraft, keep that in mind as we talk about some of the science. The first part is thinking about the science traceability matrix, which I've taken a screen grab of here. Are these the right questions we're asking? Are there important questions that we're missing? Yeah.
Kirby, could I jump in? Maybe others want to as well.
Please.
Before we start going through this, one of the things that I found, I hate to use a negative word, but I'm going to use the word disappointing yesterday, is the notion that we can only get one flyby on the way out of the solar system. In fact, If there's a planetary augmentation, um, it's likely to go to a dwarf planet. And anytime you go to a dwarf planet, you can get small planetesimals along the way, more or less for free in the noise, as long as you bring a little bit of fuel along to make it possible. And so I think the STM and the whole write-up that you're talking about should talk about a mission that does a combination of a dwarf planet plus one or more MU-69s, if you will.
Mm-hmm. Okay, thank you. And you know,
it's really easy to get the little ones. And even if we pick a trajectory, let's say that goes like some of the ones discussed yesterday, that's optimized for solar probe, let's say it goes 90 degrees. So it goes due north. That makes it hard to get a dwarf planet, maybe impossible, but you can still likely get one or more planetesimals.
okay. Yeah, and I know Brian Holler, I think he's on this call, has made that point in a few of his conference presentations. As KBO observations ramp up with new ground-based telescopes like the LSST, we'll get more of those. And Alan, I hope you're right. I don't know. You know, I'm you know, the trajectory folks. Yeah, you know, of course, it's a question of fuel. And if we had to do one thing, it would be, in my view, a dwarf planet. Get one of the big ones.
Yeah, so fuel's a lot cheaper than instrumentation. So if you can afford the instrumentation, you can afford the fuel from a dollar standpoint, making the tank a little bigger and hydrazine or whatever you choose for the, if it's a biprop, fine. But I really think we have to really push on this, because that's the way that the Planetary Division comes in the game. And that's the way that you get the planetary decadal excited about this.
Hey,
I think Alan's
I
exactly
know,
right.
right?
And in fact, I would hope that we could, go ahead.
No, go ahead, Casey, you're on.
Oh, I was going to say is that Alan's exactly right. I would hope that we could fly by a Centaur as well as a KBO. The larger ones makes life easier for your dwarf planet. I also want to say one other thing that Alan has already touched on, and I want to bring you back to the question of composition. Your camera is mainly going to be getting you, you're going to get filter ratios. So you're going to be able to do what with the upside down woodpecker and get ideas of colors that are telling you different things on your dwarf planet. But I want to remind you is that the astrophysics folks, we're going to talk about this a lot on Thursday, are baselining or speccing an instrument that is going to get you 0.5 to 15 micron imaging spectroscopy. Okay, it's the Vizier mapper. And it's also going to have far infrared bands that are going to get you temperatures. It's going to get you maps of this object if we actually put it in the right place to do it. It's going to be LISA plus, and it's going to be Rex plus in New Horizons terms. And I want to, now the reason you may not be talking about it is because we can probably expect the funding for that to come out of astrophysics, not out of planetary. And it's going to be a stovepiping problem. But I want to break those stovepipes because there is absolutely zero reason why we shouldn't use that instrument during a flyby to augment the science you're talking about with this imaging camera. Everything should be multi-purposed and tasked because mass is such a limitation. So I behoove you to actually work that in. And I thought we did that with the STM and the way we designed the questions.
Yeah.
Because that gets you the composition. It's what Alan said. You're going to optimize your camera for geomorphology and shapes and structures and heights, et cetera, but you're not going to optimize it for spectral capabilities. And so that's why you have a spectrometer that may be lower spatial resolution. And that's why we combined the LISA maps with the LORRI maps on New Horizons.
Yeah.
And that was really powerful.
So are you saying that within the context of the Helio Plus or to the full planetary augmentation where it's a 3-axis control?
I think this is, I'm sorry, I think that, I would like to see 3-axis control, if you ask me. I think we should do exactly what New Horizons did. We should spend most of our time spinning, but we should have the capability. There's a reason why Allen and company built New Horizons the way they did with the ACS control system they did. They knew wheels were going to be too heavy and not necessarily going to last the duration of the mission. Yeah, I'm all for it. The 3-axis stabilized when we need it. Yeah.
And so maybe I should rephrase that in that context where we've got the full planetary augmentation with basically Ralph plus on New Horizons plus this what Casey's talking about, this thermal IR mapper that goes out to what, 50 microns?
It's a 0.5 to 15 high resolution spectrometer, and then it'll be 4 bands, 30, 40, 60, and 100 microns, just big fat photometer bands.
Yeah. Great. Yeah. And so, okay. So keep that sort of capability in mind going through the STM. Are these the right questions to ask? Should they be edited? What questions are we not asking? I, for one, am curious about the issue of planetary atmospheres on planets that probably don't. I mean, Quaoar and Gong Gong from Earth-based observations have had, you know, upper constraints on their atmospheres that are ridiculously lower than Pluto. I don't have the numbers off the top of my head, but is it worth putting something like a UV spectrometer for something that may not, to measure something that may not even be there? That's one question.
There's already going to be a UV instrument on this spacecraft.
Well, Lyman Alpha, right.
Yes, and a Lyman Alpha instrument can do a fine job of basic characterization of whether there's an atmosphere or not.
Good to know.
Exactly.
Thanks, Alan. I'm glad to know that. I was hoping a UV guy would speak up.
Good.
Okay. Yeah,
This is Don. Can I ask a question?
sure.
Well, relative to Alan's favorite topic of how you define a planet, what is a dwarf planet? Somebody mentioned 130 dwarf planets yesterday. Is that just a prediction from a model?
No. We know of today 130 bodies in the trans-Neptunian region that are 400 kilometers in diameter or larger. There are probably many, many more, but those are known dwarf planets that exist.
Greater than 400 kilometers diameter.
Yeah, greater than that. Yep.
So that's on the minor planets list. And
Yep, they all have designations, and yeah, these are real planets that you can go look up. 130 of them, 400 kilometers and larger, and there's a lot, you know, in that, you know, Arrokoth, MU69 is like 35 kilometers in size, and there's this whole size gap of a few hundred kilometers, you know, up to, so 400 kilometers is kind of where things start becoming round by self-gravity. But, you know, lower than that, there's, you know, way more. So, you know, there's a lot of trans-Neptunian objects out there for flyby targets. And even if you're just interested in dwarf planets, there's still a lot of those as well.
so relevant to Alan's comment, I mean, it's certainly possible to get targets of opportunity, but to get a dwarf planet, you would probably have to target that as part of
That's right, John. You have to target it, but there are quite a number in the Kuiper Belt, and so there are a lot of choices that go in the general directions that the heliophysics community wants to go. So I don't think they're incompatible at all.
That's right.
It's most likely we'll get a scatter disk object, which we haven't visited yet, if we go a little bit off the plane.
Yeah. I mean, the idea is that the heliophysics community picks the general flyout direction, and then we pick a dwarf planet that's close to that and tweak the trajectory to target that for a close flyby.
Right.
And I like the idea of going to a somewhat bigger one because it improves the mission success criteria. If you remember, MU69 was quite challenging to make sure we imaged it properly at the flyby time.
Right.
And bigger means it's easier to shoot.
This is the most important point, though. If you go to a dwarf planet, picking up small primordial planetesimals before or after is essentially for free.
Mhm.
You will get them, period.
All right, Alan, thank you. We'll work that into this
It's
document.
also the case that you'll get them if you don't have a dwarf planet, you know, as your centerpiece.
Sure. Yeah. So feel free. Everyone is free as I'm talking, as we're talking, as we're discussing, to go pencils up and start editing this document. Just kind of scrolling through here, showing you what's here. Do you have any comments on mission success criteria? What are your thoughts on the nose camera versus what you could do with the full planetary augmentation that has better imaging capability and much, much better pointing capability? Is this worth doing? If it is putting a nose camera or nose imaging spectrometer on here worth doing if we can only image on approach, in your view? You know, some other issues. What are your thoughts on data allocation? Based on a previous work that Alan and I have been involved with, you know, New Horizons took about 30 gigabits worth of data at Pluto if you combine the data from the Ralph camera, LORRI, and the Alice UV imaging spectrometer.
Actually about 50.
50.
No.
Okay. Okay. I was going back to old emails with Candy. Okay. And that's plus or minus 150,000 kilometers of the target. For distant KBO observations, that's something that the interstellar probe could really do, is something that New Horizons has been doing high phase angle observations of distant Kuiper belt objects that are not resolved as disks. You can still get unique photometry, rotation information, and spectroscopy on from the Kuiper belt.
How distant is that?
Alan, I mean, it's you know,
John,
millions of kilometers, you know, basically
We have
arbitrarily
observed,
far that you can't resolve.
we've observed Kuiper belt objects in the distance as far as 100 astronomical units away and as close as inside of a tenth of an astronomical unit with New Horizons. Kirby, can I suggest an implementation
Please.
for this mission?
Please.
So if the heliophysics community wants a spinner, and I'm certain they do because they want to deploy long booms and antennas, it's really hard to do the planetary job as well as you would like to. And you're doing a brilliant job of showing ways to sort of make it work. What I think the best implementation for a mission that does both is to have a single detachable small planetary spacecraft, 3-axis spacecraft, that rides along with, undocks from, conducts its flybys, whether it's a small KBO or a Centaur or a dwarf planet, and then docks back with the mothership. We have this technology. We're using it all the time in Earth orbit to do automated dockings without any human intervention whatsoever. We should be using it for a mission like this. And then what you can do is you can achieve an optimized planetary mission without compromising the heliophysics and vice versa. And further, then you have a very clean interface on the budget. Planetary builds the little 3-axis guy that detaches for the flybys, and heliophysics builds the mothership that doesn't have to become a planetary spacecraft a few days in its life.
Okay. Alan, can we follow up offline, or even in here? I would love to learn more about that Earth orbit capability of
Yeah. Did you watch the Dragon last night?
Yeah,
Yeah, that was a totally hands-off docking.
sure. Oh, okay. Yeah.
Much more grandiose and expensive than you need with robotic spacecraft. But there's plenty of robotic instantiations in Earth orbit that are used for everything from nefarious purposes to satellite servicing.
Okay, great. I'm taking notes the old-fashioned way, but I hope some of these also. But we'll get this into the Google Doc as well. Thank you for that.
And also, just to amplify on that, Alan said exactly what I was thinking. But also, I thought the DART mission doesn't it have a little Italian provided camera that is going to separate from it and take pictures as DART comes in? Or is it
Yes,
that camera still on the spacecraft? At least that was the original plan.
Yes, that is the case.
So there's another example. There's a space, there's an actual NASA exploratory mission that is doing that two-parter as well.
Right.
And that way, I think it's a cast-off. That little mini sat is not going to come back to the mothership.
No, it's not.
Right.
In fact, the kick of that mini sat is a significant amount of meters per second. So, because it has to get away from the target. So you would need a very, 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 very soft undocking, or else the drift between the two satellites is going to get untenable to return over time.
Assuming we're going to be spinning, one thing that I heard that I wanted to make a little correction on that we probably would want to look into, JunoCam is not a line scanning camera. It's a push frame camera. The frames are about 1600 pixels by 155. And if you've ever assembled some of the noodles, it takes little frames simultaneously and then strings them together. And so looking at the trade-offs of that versus a line scanner would probably be something we would at least look at.
Okay. Thanks, Ted.
I'm not exactly sure the reasoning behind that design, but figure it'd be a stone worth turning over.
Well, Ted, you've got more experience than most people on assembling spacecraft images, so I'd be happy for your help on that as you're willing.
And Ted, is there any smart way that one can actually use, you know the spin rate, right? So you know, if you will, do some Fourier transforming. You should know how pixels are moving around and as you're looking at something that's going, and you should be able to reconstruct with some fancy math, or is that not possible?
I mean, with a line scanning camera or a frame scanning camera?
Frame scanning.
With frame scanning, yeah, it would be, it could be done with either, but that would, with the way Juno Cam does it, doesn't really matter where you are on it, but that would be an issue with this with a nose camera like this. You know, Juno Cam pretty much just sweeps across the frame, and so but we would have that issue with the nose scanner, that there would be some variance across the image.
Kirby, did you have any tall poles in the STM that you thought, or something that was not complete, you thought you'd want the group to consider?
I've scratched my head bald thinking about it, but that's why I think the outstanding question is maybe an issue of ranking priority. If we, geophysics and composition, planetary astronomy, distant KBO observations, planetary atmospheres are, is there a priority level that we could suggest? And I hate to call it a D-scope list, but almost what it becomes by default. I know there's a more diplomatic way of saying that. I don't know what it is. But as a geomorphologist who knows enough to play a spectroscopist on TV, the geophysics and composition question of the STM is, to me, the most compelling question. What do surface compositions, planetary shape, and geological landforms reveal about the current state and evolution of KBO and dwarf planet surfaces, interiors, atmospheres, and potential to support life? So,
So, Kirby, I often said that the purpose of New Horizons was to get LISA to Pluto. That more than any other instrument, it satisfied a greater swath of our objectives. And had we only had the LISA data set, we would still have maps of the geology. We would have infrared colors and infrared spectra at whatever it turned out to be, hundreds of thousands of locations. I would put an infrared mapping instrument at the very top of the list because it would give you geology. And then I would do an optimized camera after that.
Okay.
And then if you're hard over on the atmosphere, the Lyman alpha can't do everything, but it's a poor man's substitute.
Sure.
For some things. But even without a spectrometer, a couple of simple photometers in the far ultraviolet can do things like give you altitude profiles of CO or nitrogen, etc.
Okay. That is very helpful to know. And I was wondering that myself, if Lyman alpha could give us at least some of that. Good to know. Thank you.
Now, Mihai Hirani claims that if you have a dust analyzer, which is part of the interstellar probe payload, that there's a very good likelihood, if not a certitude, that you will encounter sputtered dust grains on a flyby from large objects like dwarf planets and can analyze their composition.
Yes.
And I don't know the numbers to back that up, but Mihai Hirani is the go-to person on that. Or
that would be great, Alan.
Other people in his group, like Sternovsky, for example.
So, Alan, we didn't see any dust in the Pluto system. Is that because you think Pluto had an atmosphere?
Yeah.
But we see it for a dwarf planet without an atmosphere.
Well, remember, we don't have a very sensitive dust machine compared to the kind of things that are being talked about for this mission.
That's true. So, Kirby, and to riff off of what Alan just said, that's another instance where you have a baseline heliospheric, baseline threshold mission, but heliophysics instrument, but it could certainly be repurposed as a strong word. It could certainly be used to get good planetary flyby science as well.
Yeah, that's where maybe some input on the STM would be good, because Casey, I mean, that part, the whole dust part is stovepiping. It's not in the planetary part of the STM. It is in the STM though.
And the heliophysics community is used to this. For example, Solar Probe is making multiple Venus flybys and being repurposed at those flybys to use the sensors that they do have to learn things about Venus.
Casey, do you know on the astrophysics and dust STM, which I know we're talking probably about on Thursday, right?
Yes, we will be talking about it on Thursday. Go ahead.
But I mean, you know, those STM questions aren't on the tip of my brain, but maybe they're on yours. Is it just a dust counter, or is there like a dust composition analyzer on that part of the STM?
To answer your question directly, is we were planning on flying a dust analyzer. We're recommending it. Remember, we're recommending. This is not a proposal. Right. A D-scope is to cut it back to a dust counter like the STC on New Horizons. We are certainly hoping for a lot more because there's so much more science to do here. A simple dust counter will not do anything near what you can't tell whether ISM dust is different from dust in our solar system, ice rock composition. I can go on, but I should wait. That should be Thursday. The thing that I'm hearing now, which I had not appreciated, and maybe was that Alan's pointing out that collecting dust near a dwarf planet could be critical to planetary science, and I had not thought about that. That's not in the STM at all. And that's certainly
I only get credit for reporting what I've been told by Harani's group.
Okay.
They were petitioning to be on a mission a mission proposal that I led, and so I heard them make that proposal.
Well, so because we're trying to avoid the stovepiping, Kirby, if I may, this belongs in the planetary section of the STM.
Yeah.
It's not the instrument that this is, the STM is broken up, it's the different science themes. So I think we need to write in a dust collection using the IDA. That's actually the implementation. We need the bigger question, which would be the composition of the dwarf planet. How does it compare to other dwarf planets and other KBOs? This is totally off the top of my head. I'm sure we're going to rework this.
Mm-hmm. Yeah. No, just.
What is the composition of our dwarf planet versus the ensemble of TNOs or something like that? But yes.
Yep, I love it. Yep, that's a glaring omission, and I like this. It's
why we talk.
It's ground truthing spectroscopy.
And you may want to just add a note that we should ping Mihai about this.
How do you spell it?
Mihaly, M-I-H-A-L-Y, Horani, H-O-R-A-N-Y-I.
We'll fix it. Just make sure.
Yeah.
Horiani. It's very Hungarian.
Okay. Well, it's a Google Doc, so anyone can edit it and fix my spelling.
Yeah.
Okay. For distant KBOs, searching for distant KBOs with very far aphelia, planet in the planetary astronomy part of this, what do small, let's see, where is it? With regards to distant KBOs, are we asking the right questions in terms of?
Do you mean search from the spacecraft? Because
Yeah.
I don't think we have the bandwidth to do it, to send the search images back.
Well, lower down on this list, we can talk about that, where we talk about data volume. That's a trade that can be considered is, yes, we could do it, but here's the data volume cost for that.
I don't think it's practical from the studies we've done for New Horizons.
Okay.
The data rates are out of bed by orders of magnitude.
Is that something you feel that some kind of onboard processing that New Horizons doesn't have could help?
Well, we're adding that onboard processing to co-ed images now. It'll be on board by next summer.
Okay.
But it doesn't solve the problem. The science that I'm not seeing here, maybe it's just because we're only seeing part of it, is studying the satellites of small KBOs and dwarf planets. And particularly for the planetesimals, the study of the satellites can be as important as the primary. And in the other meeting that's competing with this on planetesimal formation, there are lots of talks and lots of threads about what the satellites can teach us about planetesimal formation. So we really need to make sure that that's a part of this story. They're separate from, and probably more important than the atmospheres, in that we know that almost every KBO probably has satellites.
Yeah. Thank you.
And one other point that I remember Alan taught me a while ago during one of our STMs at APL, if you get a satellite and you find out its orbit, you get the mass of the primary. And that's a very critical, because we're not going to have a mass detector on this on ISP. So that's a very important measurement if we can find a satellite or a moon.
I wonder, is there anything that we can learn about the NEAS model of the solar system from studying the composition of the dust to put this in also in an astrophysical context? I know I've asked this question before, but now we've got the larger group.
I think that's going to be tough to say anything decisive, Abby. Just space weathering effects alone that affect these surfaces, bias the sample or composition of the dust, or evolve it rather from its primordial composition.
Okay, I'll just plant the seed there. Have a think. Assembled minds. I also, I put this in the chat. You were saying about how data hungry it was to do those all-sky surveys, Alan, from New Horizons. I wonder if, because we're spinning, maybe we can come up with an imaginative solution where we, because you'll see the entire sky, you could sum that and then telemeter that once every 10th spin or something like that. And if in any of it you see a line, then go back and explore. For example.
I'm following you, Abby. What is the scientific objective that you're trying to describe?
Well, it was to discover new, what was it, Kirby, that you wanted to do?
This KBO searches, but it sounds like the data volume for that per image in the stack is pretty big.
Well, there's also, Abby, I don't think you're allowing for the confusion noise. If you haven't, well, for DKBOs on New Horizons, we've found an object and we've stared at it for thousands of seconds and done a lot of deep stacking.
We find them from the ground.
Yes.
Or in some
Okay.
airplanes.
So imagine the scenario, the KBO is there, we're tootling along here, we're spinning this way, I'm taking a picture of this KBO, and maybe I take it 1,000 spins. I take it once every 1,000 spins. I only have to telemeter one stripe of data, and I'll have, if I have a smeary light in it, then I'll say, oh, hang on, let's start doing that, a bit more seriously for the next 1,000 spins.
That'll get you the bright ones, but not the faint ones that are down in the confusion noise.
Turns the flux out over a lot of pixels, so you're getting a lot of read noise from that, so you wouldn't be able to detect very faint objects.
Right.
So.
Okay, another seed to consider.
But you might be able.
With the advances we have in data processing and a lot of the things we've learned from Juno Cam, I do think there's a lot of advantages and a lot of interesting advances to be made by trying to understand how to get the data back from the spinning spacecraft. And the more I've heard from the Helio side, the more I'm doubting that we're going to get a partially despun or a despun platform. So
that's why you want Planetary Division to play in and to build a daughter satellite.
I love that idea. I sketched out the picture you described. It sounds incredibly sci-fi, but I appreciate the confidence you had. I'm going to look into that.
And Alan, I liked the political messaging on there. It made it very easy to fund it because it was well-defined stovepipe. That was something I hadn't thought about. That's good. So we're at the top of the hour. We have this Zoom room until 2:15, but in the spirit of Janet Vertesi, who I don't think has joined us this week, I wanted to open up the floor to any early career people defined as within either still in school or within 10 years of your degree. Just to give a chance to share some thoughts or ask questions.
Don't tell me you're the youngest person around, Kirby.
No, that's Charlie.
Hey everybody. Probably my Zoom is going to get my audio eaten. Sunny Harmon here at Ames. I think one of the things that, and I keep harping on it because, I'm a one-trick pony, but it's definitely something that I've been thinking about a lot is what you can do with the cameras that we have when we're not sort of nearby. a lot of these other objects. And I know Kirby and I have talked a lot about the intersection between sort of long baseline observations or retrospective observations of the solar system planets. And I think potentially with like a nose-mounted camera, that makes it easier potentially to access some of those other viewing geometries and not have to have an independent observational platform to do two, complementary observational strategies. So I definitely think there's a lot more synergies there that potentially could answer a lot more sort of broad scientific questions potentially.
It does reduce the field of view for, the potential selection of objects, right?
But you're staring at the same field of space for the entire mission, essentially, and you're flying through that field of view as well, since it's in your RAM direction. It occurs to me.
Can the spacecraft be turned while it's spinning?
No.
Yeah, so like maybe 180 degree, and then the forward-facing camera becomes a rear-facing camera.
Exactly. And can you use your look back camera, your idea with your Fly's Eye 3 color to do all your planetary imaging as well?
Who would know the answer to? I heard you, Kirby. Do you know that that's true? That you can't reorient a spinning?
If you've got a helio spinning, I mean, Gabe can jump in, but if you've got a helio spinning spacecraft and you're requiring on the centrifugal force to keep the whip antennas taut, you're not going to rotate that spacecraft any other way.
Well, you can. It just uses an incredible amount of fuel and takes an incredibly long time. So,
which means
I mean,
can do
there's one thing, we have time.
Do anything given enough time and money. So
it's a lot simpler to just put another nose camera facing the other way.
Oh, good point.
Try and turn a giant spacecraft like that is
a lot of risk. Yeah.
As Gabe is trying to describe to you, that's.
Yeah. The other thing is if you had a camera on a essentially a gimbal platform that flipped 180 degrees.
Right.
Which would probably be more tenable.
But the issue with, yeah, but of course, if the spacecraft is spinning, you've got other complications the mechanical engineers won't like.
Mm-hmm.
It's easier to just have one fixed forward and one fixed backward. Also just go back to my favorite implementation. If you have a detachable daughter spacecraft, there's no reason, if it's reliable, that it can't attach many times, even in cruise, to do things like this. It doesn't have to just be for flybys.
So, Alan, we've chatted about this for a daughter spacecraft, and it keeps coming down to power, communications, and propulsion for a very small spacecraft, and how near-term and pragmatic that is.
So if it's truly a daughter spacecraft, it ought to be able to run on batteries because when it docks, it'll recharge. Secondly, for communications, you're talking short range. You're never going to go very far from the mothership. Maybe kilometers, maybe less. Communication, or it can just store the data, and when it docks, it can download it over a connector.
So you can have a wireless, probably not a Bluetooth, but a wireless data connection.
And that is common on modern spacecraft.
Alan, I like the idea of the daughter spacecraft because it's easy to sell to headquarters as a move. Basically, you're hitching a ride on ISP for Planet. You tell that.
Exactly.
But the mechanical interface and all the interfaces between the docking bay and the mothership.
So Planetary should pay for that, not Helio.
Okay. But the problem we heard about yesterday, right, is that batteries aren't going to be like a long-term solution, right? I mean, this is definitely, you are doing potentially daughter craft operations within the next 5 or 10 years after launch, and not necessarily on the sort of 40 to 50 year time scale you might need to get some of these KPOs.
And I would guess is the way you're going to want to do it is you're not because there's a risk the daughter craft may never go back and be able to rendezvous successfully with the mother craft. Maybe you, from a risk point of view, you don't detach the daughter until you do your main flyby by your dwarf planet, and then you keep using it for a while. Because nobody's ever done this daughter mother far away from the Earth. I'm not saying it won't work. I'm just saying is just think through the risk posture. You'd want to make sure it gets primary planetary science first, and then you can try to keep reusing it.
Interesting.
I'm not pushing that. I'd like to use it the whole damn flight, but I can imagine the engineers pushing back. very hard.
Do people want to be mean and nasty, and by all means do, about the rotational push frame or time delay integration concept? Is that a non-starter? Could it work?
It could definitely work. It's not going to be up to, obviously, a 3-axis stabilized spacecraft, but I think we probably have more of a chance of, to borrow from something Alan said, it's better to get part of something than all of nothing. And if there's no other reason besides Planetary to have 3-axis capability, and we can't have a daughter spacecraft, then it's probably what we could get.
Mm-hmm.
So it's not completely crazy to have a curvilinear time delay integration.
No,
I've never heard of this ever being done.
Same.
Like you ought to look into whether it's ever been done.
Yeah, you want high TRL. That's why I would keep pushing the Juno experience. But Kirby, I also want to, before we go on, I want to back you up. I think the fundamental thing for you to think about is what resolution do you need on the surface in order to do good science? Can you live with 2 or 5 kilometers per pixel? 1, of course, is much better. But what is the minimum you need in order to do transformative science on a dwarf planet? And then we can start thinking about what instrumentation, what
right. I've been thinking 2 kilometers as a, I'm a geologist, but that's about the worst. I mean, I'll take what I can get on the one hand. On the other hand, I'd like better than 2 kilometers.
No, you're not being held. You're not going to be held to 2. I am working on multiple GWST proposals this week, and people are asking me what resolution I need in order to do the science and to figure out the different materials in the object we're looking at. And I keep telling them I need 20, SNR of 20. They're pushing me down to 10, but I can't do it below that. So we need the same kind of answer from you. If you really, yes, we understand. If somebody holds a gun to your head and if you can work with 2, that's the number we need to start from.
Okay.
I mean, if you say, we say, well, we can get you 5, and you say, don't bother, it's just not worth it. That's what we need to hear.
Yeah. So I've been thinking I would like, 2 kilometers or better. Preferably less than 1 kilometer. I think that's very doable.
One thing that would be nice, even if it were a lower resolution, side-looking camera for closest approach, to get some kind of lower phase angle, kind of in the medium phase angle range, to get a better idea of topography, and also to just get a look at some different phase angles. That would really be, I think, an enhancement over just having the front-looking camera.
Ted, it looks like you added that as a note at the bottom of the list. Okay, good. And are you talking like a really wide-angle camera for something like that, like
probably? Yeah.
Where you're looking tens of degrees field of view?
Yeah, possibly. If that's all we can get, it would be better than nothing.
Mm-hmm. So you want a whack and a knack combination?
I'd love a whack and knack combination, but I'm also feeling very constrained by the engineering and pragmatics.
I think the mass constraint is you should go for a knack that you can bin up.
Yeah.
I think one of the things we'd like an answer to then is if Planetary were prepared to pony up money for it, what is the limit from the heliophysics payload on how much we could offer? I presume that the weight of the spacecraft defines the speed.
Yeah.
I know that it does from our presentation. So yeah, how big is the box that they would be prepared to take from Planetary if we were to be able to find the money?
Well, there's someone said, I think it was Jim, there's about a fairly linear relationship between, for every 50 kilograms of mass you take off or lose, that's a 0.17 AU per year change in velocity.
So notionally, Abby, about 10 kilogram instrument, roughly speaking. If you get to 20, that's very, very big compared to the
But that's 10 kilograms, including everything, including the accommodation component on the mothership.
Yes.
Or 10 kilograms of whatever it is.
There's a little bit of savings, Kirby. If you need a lower resolution, I know you don't want to hear this, but if you go to lower resolution pickles, your primary telescope can be smaller. You can save some mass.
Okay.
I just want to point that out. I'm not pushing you towards that. I resist it myself, but it's a reality that if something is better than nothing. you could reduce the primary on a Lori light camera a little bit if you needed to. You could go, if you wanted 2 arcsecond pixels rather than 1 arcsecond.
I think in microradians and you think in arcseconds, Casey. Ugh.
5 microradians is an arcsecond.
Okay. Gabe, I don't know if you're being sarcastic. Fun problem to think about in that a mother-daughter ship changes the spin axis. The principal axis.
That's
Yeah,
true.
I'm just was getting into a small technical comment about things we need to consider. I don't want to try and design anything here during this discussion, but I just wanted to bring up an item. So
Yes, that is fun to think about.
Well, if I remember, the model for Juno Cam was that, if I understand, it was a donated instrument from the Discovery Channel. They had to pay for it, and they had to make it very low footprint in terms of risk and mass, et cetera, to get onto that spacecraft. Can we promise, given current technology, roughly the same for a daughter spacecraft? I think we can, but we have to be, are things mature enough to do that? And that goes to Gabe's point, was there is a footprint, because if you detach the mass, you're going to change the spin. That's one.
Not if you dock along the central axis of the spin, which is the way to do it.
Yep, that's the easiest way to come off
Yep.
it at low speeds.
It's a cool idea.
I just did a little calculation in my head, which any of you could do. But following Kirby's numbers, roughly 0.2 AU per year cost over 50 years, works out to 10 AU. 10 AU out of 1,000 is 1%. That seems like a very, very small cost.
Yeah.
10 kilograms.
Yeah. So even if it was 50 kilograms and you took 5% off the final distance, or you just took you 5% longer, 52 years, 52 and a half to get to 1,000 AU, it seems like a great trade to bring in a whole nother constituency to make this heliophysics mission happen.
Or just to have a second Pluto-like flyby. I'm preaching to your choir, but yes, that would be fantastic science. I'm not sure whether they're very sensitive to the flight speed though, Alan, just to say, the Helio guys. Because they were aiming for 10 to 20 AU per year, and we're now down at 7.6.
Well, that question that I've been, that I used to say when I was at headquarters about, do you want 80% of something or 100% of nothing, mainly applies to budget. And I think for heliophysics, teaming with Planetary and/or Astro is the key to getting this mission to happen. So they need to give up a little to get a lot. Because the alternative is you get exactly nothing because the mission never flies.
Well, the way we got this study approved, or at least in the current phase, was to go down to headquarters and show all the rich planetary and astrophysics science we could do. And it wasn't just Helio.
Well, you're just making the point stronger. I agree.
Yeah. Oh no, I'm agreeing with you. No, I'm very agreeable. That's exactly what we did, and they heard that. They have since then tried to make this more heliosphere centered, helioscience centered. It's not clear what that's going to be next year, but
in our last minute, I'm really grateful for the discussion here. In our last minute, in the coming weeks and months, the engineers are going to start working on a planetary augmentation actual CAD design for an actual spacecraft that could happen. And so that's going to be happening soon. And we'll be reaching out to this community for more input periodically. And so, and Alan, I always love hearing your perspective from being in the thick of it with New Horizons over really the last 26 years. Is that right? 31 years. Yeah, so there's so much to learn from you, and I really appreciate that. I did put the link to the networking event in the chat that James had posted earlier. I'm going to hang around in this Zoom room for a bit longer, but just wanted to encourage people to head over here to this networking session.
And can I remind you that we can carry on a similar conversation in the exoplanets outbreak tomorrow? Breakout, not outbreak. We're already in the middle of that.
Come to Abby's session tomorrow.
Kirby, I want you to take an action. You need to talk to Zemkov about the infrared spectral mapper and see if it can be nose mounted as well, or have a nose feed.
So Mike, my action item is to talk to you to see if a nose mounted spectral mapper could work.
I hope it works. Yeah, sure. You mean on the nose? I think that was kind of our preference too, except real estate up there is expensive, so I don't know. But yeah.
Now you've got really big pixels, so is the spin rate of the spacecraft a problem?
It will have a scan mirror in it to compensate, but I would say that's TBD because it depends on what the scan rate is and things like that.
What if the motor on the scanner breaks after 10 years?
That would be a problem.
Okay.
Although I would say that, I mean, it depends what the mission is, right? I think that after it's done, whatever asteroid's going to do in a flyby, you probably turn it off forever so you don't care anymore. It doesn't need to last 50 years.
Well, that was the point. Yeah. What if it breaks before half the mission is over?
Yeah, I think that's fine because we're done by then probably. Plus, you know, the data rates for this thing are so prohibitive that the further out you go, the less you can do. Basically, that's what it boils down to. Sorry, I was just in the lab helping students and paying half an ear, so I missed some of this. I apologize.
No, you're good.
Yeah.
I'm glad you can have students on campus and get some work done. That's great. Once again, please write down any thoughts in the Google Doc. It'll be open until December 1st. Let us learn from our collective wisdom. And I think people are starting to trickle off into the networking session, but I'm happy to hang out here.
That's the virtual chair one?
Yeah, virtualchair.net.